One of the great storytelling devices in thermodynamics is a PV diagram. PV diagram means that you have pressure on the y-axis and you have volume on the x-axis. The pressure and volume relate, of course, using ideal gas law. The product of P times V will always equal NKT. Now, most of these processes involve sealed containers, so that we don't have to worry about N changing, which means the product of PV can be found on the graph at any time, and so can the temperature. Now, if you want to change the temperature or change the energy of our gas, we can do that in two ways. You can do it by work or heat. And these diagrams will tell us how it is that we've changed the temperature or the P or the V in our system. So if we look at this process AB, you can either go from A to B, or you can go from B to A. So let's think about the process B to A. As you go from B to A, the volume is getting less and less and less, yes? So less volume means that you have compressed the system. Compression. So here, as our work is being done, work is negative P delta V, or a force times the distance of compression. As we compress the system, the work on the system is going to be positive. If we add work and we don't allow any heat to leave or enter our system, because we are in like a thermos, something that's insulated, then we can see the energy quantity of our system will go up. So you can also calculate the corresponding temperature at any one of these locations and the amount of work being done. So when you say compression, I know the work done is positive. Instead of using these numbers, which are finite, you can take the area of our graph, which is work, P times delta V. So we'll replace this idea with work in these diagrams as area. Okay, next you can find the temperature at either location A or B. Well, how would we do that? You would just say T is P times V over NK. And you might not know NK, so you might only be able to talk about what T is proportional to. Well, T over here is PV over NK. So the PV values will be of different types. So if we put some numbers on here, you see that this 2 times 4 is a PV value product of 8. Well, 5 times 2 is a PV value product of 10. So these are telling us that the energy or the temperature has changed. The last equation that we keep in mind when using our PV diagrams is that energy is proportional to 3/2 NKT, or 3/2 PV. So anytime the temperature goes up, the energy goes up. And the diagrams will show us whether we do work to increase this energy or add heat to increase the energy. Let's first look at a system that keeps the temperature or the energy of the system constant. This is called an isothermal process, and the curve itself is referred to as an isotherm. So if the temperature is going to be constant, that means the product of P times V needs to be constant. And N and K will remain constant because we're going to have a sealed container, and K just is a constant. So here, if you solve for P, then what we have is P equals NKT over V. This is a hyperbolic function. So a isotherm is hyperbolic. It keeps the same temperature the entire time. Follows a curve on a PV diagram that looks like this. Okay? In an isothermal process, the delta U will not change. Because remember, energy, as stated above, is 3/2 NKT. If the T cannot change, the energy cannot change. So that means as work is being done, then the exact amount of heat will have to be allowed to leave the system so that the delta U will become 0. Okay, let's go ahead and watch as the volume in a system gets changed. The volume will get compressed and the pressure will increase. Then you'll see the volume increase while the pressure will drop, remaining the same temperature of the environment the entire time. The micromanometer is going to detect the pressure in the bottle. So you can see as the volume decreases, the pressure increases, thus keeping a constant temperature. The next process that we're going to look at is called adiabatic. No heat can escape. This is called adiabatic compression or expansion, and is this line here. So as we expand outward, as we expand outward like this, our temperature will actually drop. So an adiabatic curve will always connect two different isotherms. Adiabatic curves will always change temperature. Well, why does an adiabatic curve always change temperature? Well, let's expand on it. So if your temperature is proportional to U, 3/2 kT, and you can change U by working or adding heat. The definition of adiabatic is that we won't allow heat to be exchanged. We will only allow work to be done. If you expand like this, then we are going to decrease our pressure and increase our volume. What type of work is that? Well, you really didn't do any work, right? Work is negative P delta V. So if you allow the system to expand, that means the work on it is negative. Because you just stood there and watched it happen and you didn't do anything. So if work is negative, a delta U will be negative. That means temperature, which corresponds to the energy, will have to drop. Conversely, which is what we're going to watch, if you take adiabatic compression like this, that does positive work on the system, and therefore our delta U is actually going to go up if our work is positive, and then the temperature will go up. So let's take a look at that.
So the idea is what adiabatic means is there's no heat lost or heat exchanged between the interior of the cylinder and the outside world. And then
next type of curve we're going to look at is called isobaric, which means constant pressure. I say that as I can't bear it. Isobaric. Too much pressure. You'll also see this just as isopressure. You're not expected to memorize this word, but I will be using it, so it's good to kind of have a concept of what it's talking about. So an isobaric process is one that can expand a gas at constant pressure. Okay, what's required to expand a gas at constant pressure? Well, let's see. If you expand a gas at constant pressure, you'll see that there is work that is happening on the system. So as a gas expands, that means that the work being done on the gas is negative. Whoever was responsible for doing work just stood there and did nothing and just watched it expand. There's just negative work being done on that gas. Okay, look at the PV values though. Over here, right, you have the same P times a little v. Over here you have that same P times a larger v. So during this constant pressure process, when the gas is expanding, the temperature is increasing. Okay, if temperature increases, that means that the energy must go up. So how can that happen? Well, it can't happen from work because that's negative. So it's got to happen from adding heat. Let's try it out. I took a sealed container under atmospheric pressure and I put it into boiling water. You can see that the volume of the container is expanding as the temperature increases and the energy of the system increases. So you have isobaric expansion right there, but we can also have isobaric compression. And what would that look like? Well, if you're going to have compression, that means under here, the work being done on the gas is going to be positive, and your temperature value is still going to drop. So as we compress, our work on is positive, but our temperature decreases. Now, how can that be if the change in energy is proportional to temperature? Your work is positive, so that means that you need to take away a lot of heat, right? More heat than work done. Let me show you how to do it. Here's bubble in the freezer. Look at how wrinkly the lid is, as it's all sucked in. Okay, the last process, isocuric, also called isovolumetric, which means done at a constant volume. In this process, you'll realize there's no P delta V. There's no work that can be done. Okay, so what's happening in this process? You go from a large P, V value, to that same V value, but with a small p. So in something like this, temperature is changing. So let's do this with a temperature increase. I'll show you. So here, we're going to go ahead and increase the temperature, right? Temp is going to increase. How are you going to do it? Well, you can't increase the energy or temperature by doing work because there is no delta V. Bloop. So that's not going to happen. But you can change the temperature by adding heat. Now, it's been very hard for me to do this in my house. To change the pressure, I've really just been using the pressure of the atmosphere, which is constant. So I had to get a little creative. Here's what I have for you. All right, let's go make our standard movable top. So we've got some water over here on the stove. It's coming to a boil right now. This is room temperature air. Okay. All right. So here we've taken room temperature air and we've put it into a hot water bath, and you can see this bubble on top is beginning to rise. So we're going to add some weight to it to help squish it back down. See, it's still up right now. So let's keep adding some more weight. Ah, perfect. So in order to keep our bubble down and our system at a constant volume, we have to add a lot of weight to the lid or increase the amount of pressure. So because I don't have a pressure meter at home, I used the added weight to show you the increased pressure. I could have also fixed the lid down and the pressure would increase, but we would not be able to visually see it. Okay, so to sum up all that you've learned here, work on the system is done as a positive number when you compress the system. And work is found in the area below the process line. Okay? Next, the P times V values, which can be found for any process, will tell us about the temperature, NKT, right? These things are just going to remain constant, sealed container. So the product of P times V will tell you about T. If T increases, that means that the energy in the system would also increase, or decrease, whatever, because energy is 3/2 NKT. You may replace that fact with energy is 3/2 the product of P times V if you would like. Next, the only way to change the energy in this system, which is correspondingly the same as saying changing the temperature in this system, right, proportionally, is to go ahead and do work on the system or add heat to the system. Heat adding to the system is done by putting it in cold or hot water, while work is done by compressing or letting the system expand, right? Positive work or negative work. And those are the only two ways to increase or decrease the system's energy, correspondingly the temperature change. The processes we went over today are isothermal. In an isothermal process, the change in U or the change in temperature is 0. That means there's work and heat being exchanged. The next process we have is isobaric. In an isobaric process, that means there is no delta P, right? But there is a delta T and there is work that will be done on or by the system. The other process we have here is isocuric, also called isovolumetric. During this phase, you do have a temperature change and an energy change, but you do not have a work. Your delta V is 0, so there is no work being done on our system. The only way you can change that is with heat. And the weirdest one of them all, this adiabatic compression or expansion. In that type of system, you do indeed change your temperature, but you do so only by work because the Q added here is 0. This means it happens in some sort of thermos or isolated container.